Welcome to Chapter 12, Limits and Derivatives. This is your introduction to calculus, one of the most powerful branches of mathematics. Calculus studies how function values change as inputs change. Sir Isaac Newton, working in the 17th century, was one of the founders of calculus. As the mathematician Whitehead said, with calculus as a key, mathematics can successfully explain the course of nature. Let's develop an intuitive understanding of derivatives. Imagine a body dropped from a tall cliff. Physics tells us the distance fallen equals 4.9 times t squared meters, where t is time in seconds. We want to find the velocity at exactly t equals 2 seconds. How do we find velocity at a single instant? We use average velocities over smaller and smaller time intervals. Average velocity equals distance traveled divided by time interval. Between t equals 0 and t equals 2 seconds, the body falls 19.6 meters, giving average velocity 9.8 meters per second. Between t equals 1 and t equals 2, it falls 14.7 meters in 1 second, giving 14.7 meters per second. As we make intervals smaller, the average velocity approaches about 19.6 meters per second. The instantaneous velocity at t equals 2 is the limit of average velocities as the time interval approaches 0. This is the derivative of the distance function at t equals 2. Geometrically, it equals the slope of the tangent to the distance-time curve at that point. The derivative captures the instantaneous rate of change. The limiting process is fundamental to calculus. We take smaller and smaller intervals around the point of interest. The average rate of change approaches a definite value, the limit. This limit gives us the instantaneous rate of change, or derivative. This idea revolutionized mathematics and physics. What exactly is a limit? We write limit as x approaches a of f of x equals L. This means as x gets closer and closer to a, the values of f of x get closer and closer to L. The limit represents the value f of x should take at x equals a, based on its behavior near a. The function may or may not actually be defined at x equals a. The left-hand limit considers x approaching a from values less than a. We write limit as x approaches a minus of f of x. This is dictated by the values of f of x when x is to the left of a. Think of approaching a from the negative side on the number line. The right-hand limit considers x approaching a from values greater than a. We write limit as x approaches a plus of f of x. This is dictated by the values of f of x when x is to the right of a. Think of approaching a from the positive side on the number line. A limit exists only when the left-hand limit equals the right-hand limit. When both approach the same value L, we say limit as x approaches a of f of x equals L. If they differ, the limit does not exist. The function doesn't need to be defined at x equals a for the limit to exist. Let's find the limit of f of x equals x plus 10 as x approaches 5. For x near 5, like 4.9, 4.95, 4.99, the function values are 14.9, 14.95, 14.99. From the right, values are 15.01, 15.1. Both sides approach 15. So limit as x approaches 5 of x plus 10 equals 15. The algebra of limits makes calculations easier. The limit of a sum equals the sum of limits. The limit of a difference equals the difference of limits. The limit of a product equals the product of limits. The limit of a quotient equals the quotient of limits, provided the denominator's limit is not 0. Standard limits you should know. Limit as x approaches a of x equals a. Limit as x approaches a of x to the n equals a to the n. Limit as x approaches a of a constant equals that constant. And importantly, limit as x approaches 0 of sine x over x equals 1. This is crucial for trigonometric limits. For polynomials, finding limits is straightforward. Limit as x approaches a of p of x simply equals p of a. Just substitute x equals a into the polynomial. For example, limit as x approaches 2 of x squared plus 3x plus 1 equals 4 plus 6 plus 1, which equals 11. Direct substitution works perfectly. For rational functions, if the denominator is not 0 at x equals a, just substitute directly. If the denominator equals 0, factorize both numerator and denominator, cancel common factors, then evaluate. For example, limit as x approaches 2 of x squared minus 4 over x minus 2. Factor as x plus 2 times x minus 2 over x minus 2, cancel to get x plus 2, giving limit 4. Important trigonometric limits. Limit as x approaches 0 of sine x over x equals 1. Limit as x approaches 0 of 1 minus cos x over x equals 0. Limit as x approaches 0 of tan x over x equals 1. These standard results are used frequently in limit problems involving trigonometric functions. The derivative of a function measures its instantaneous rate of change. We define f prime of x as limit as h approaches 0 of f of x plus h minus f of x, all divided by h. This gives the slope of the tangent to the curve y equals f of x at any point. Other notations include dy over dx or d over dx of f of x. Finding a derivative from first principles means using the definition directly. Calculate f of x plus h minus f of x, divide by h, simplify, then take the limit as h approaches 0. For example, the derivative of x squared, the difference quotient, simplifies to 2x plus h, and as h approaches 0, we get 2x. The algebra of derivatives includes important rules. The derivative of a sum or difference equals the sum or difference of derivatives. The product rule, derivative of f times g equals f prime times g plus f times g prime. The quotient rule, derivative of f over g equals f prime times g minus f times g prime, all over g squared. A constant multiple comes out front. Standard derivatives to memorize. The derivative of x to the n equals n times x to the n minus 1. The derivative of sin x equals cos x. The derivative of cos x equals negative sin x. The derivative of any constant equals 0. These formulas save you from using first principles every time. Key formulas summary. Limit as x approaches a of f of x equals L when left and right limits coincide. Derivative, f prime of x equals limit as h approaches 0 of f of x plus h minus f of x over h. Product rule, f times g prime equals f prime g plus f g prime. Power rule, derivative of x to the n equals nx to the n minus 1. Problem-solving strategy. For limits, first check if left and right limits are equal. For derivatives, use the definition for simple functions or apply standard formulas and rules for complex ones. Always simplify expressions before taking limits. Factorize, cancel, and use algebraic manipulation to your advantage. Let's evaluate limit as x approaches 3 of x squared minus 9 over x minus 3. Factor the numerator as x minus 3 times x plus 3. Cancel x minus 3 from numerator and denominator. We get limit as x approaches 3 of x plus 3, which equals 6. Always simplify before evaluating. Find the derivative of f of x equals x cubed. Using the power rule, f prime of x equals 3x squared. From first principles, limit as h approaches 0 of x plus h cubed minus x cubed, all over h. Expanding and simplifying gives limit of 3x squared plus 3xh plus h squared over h, which equals 3x squared as h approaches 0. Derivatives have countless applications. In physics, velocity is the derivative of position, and acceleration is the derivative of velocity. In economics, derivatives measure marginal cost and marginal revenue. Optimization problems use derivatives to find maximum and minimum values. Curve sketching relies on derivatives to understand function behavior. In this chapter, we learned that limits describe function behavior as x approaches a value. Left and right limits must be equal for the limit to exist. Derivatives measure instantaneous rate of change, the slope of the tangent line. Standard formulas for limits and derivatives simplify calculations. Calculus is fundamental to all of mathematics and science. Thank you for joining Chapter 12 on limits and derivatives.